Hello everyone. In today's tutorial, we will look at how we can perform LED interfacing using TM4C123GH6PM microcontroller. And in this tutorial, we will first be explaining the code, and after that we will demonstrate how we can observe the output on the kit. So if you look at the TM4C123 microcontroller, it has got in total 43 pins that are available, and these pins are grouped in 6 ports labeled as port A to F, and port F in particular, which we will be using for our LED interfacing, is a 5-pin port. If you look at the address ranges of the GPIO pins, there are many registers which are associated with each of the IO ports, and they have a specific designated address in the memory map. And if you look at the GPIO port F, the lowermost address, the starting address is 0x40025000 up to 0x40025FFF. So we will be using these addresses when we are writing the code. Now coming to the configuring the microcontroller pins as general purpose input output. So these are the steps that are involved. Clock and bus configuration, wherein we ensure that we have an active clock signal. Then we have mode control configuration, which determines whether the pin is used as a GPIO or as an alternate function. Then we have pad control configuration in order to set the parameters of the drive strength, whether we require a pull up or a pull down resistor. And then we have a data control configuration to define the direction of the data flow, whether you want the data flow to be input or output. So if you see here, when we configure the first step for the clock and the bus configuration, in particular we will be using the RCGC GPIO register. And if we are making use of the port F, we have a starting address which I mentioned earlier, that it will be starting from 0x402500 for the advanced peripheral bus. When it comes to mode control, we can set to either the GPIO mode or we can set it to a alternate functionality. And if we are setting it for a GPIO mode, we can directly access the pins by the software, and for this we make use of GPIO data R register. Then for the pad control, to make sure that we are digitally enabling, we make use of the GPIO digital enable register to enable the pins for digital input output function. And finally, the fourth step is where we control the GPIO pin for the direction, whether we want it to be an input or whether we want it to be as an output. So for that, what we do is we make use of the GPIO DIR register, which corresponds to direction. So if you want to use it as an input, you need to clear the bits, and if you want to use it as an output, you need to set the bits. So set the bits means the corresponding bit which you are using should be made or set to 1. Then we have data register masking, wherein we can individually bit mask the GPIO data R register, and for this we have the GPIO ports which have around 256 unique addresses which control the specific pins or groups by using the bits 9 to 2. To explain how this masking is basically done, for example, let me consider that I'm using a GPIO data R register for port F in particular in order to make it as a data control configuration. So we know what is the port F starting address on the advanced peripheral bus, that is 0x4002500. So say you want to access only individual bits, so you need to add an offset address. So by adding an offset address, you are masking the individual bits. So if you see here, if I'm going to add an offset of 0x000 to this particular base address, there are no bits that are accessible. But if I'm going to add an offset address of 0x004, I can access the bit 0. That is because if you observe here, I have highlighted in particular the lower 2 bits in purple color, which means that I cannot change them. That is because each GPIO port has 256 unique addresses which control the specific pins or groups by using the bits 2 to 9. So that means the bit position 1 and bit position 0 cannot be used. So the lowermost two bits are in purple just to indicate that they are not used for masking purpose. It is only the bit position starting from 2 up till 9 can be used for bit masking. So that is why the offset bit addresses vary in this particular manner. So say for example, I want only pin 0 to be affected. So I need to add an offset of 0x004 to this particular base address. If I want to access say bit 0 as well as 1, set it as 1, then I need to set the bit position 2 and bit position 3, and that is why the address is 1100, which corresponds to C. So when I say bit 0 and bit 1, my actually counting starts from bit position 2 onwards. So these are the offset addresses you need to use depending on which pin you want to use in the port F. For example, if you see for pin number 3 of port F, the base address that is there is 0x4002500, and I want pin number 3, right? So pin number 3 means I need to start from my bit position 2 onwards. So this is bit 0, bit 1, bit 2 and bit 3. So if I'm using bit 3, what would be the address? The address would be pin number 3. Then pin number 3 means for port F you have the starting address as 0x4002500, which is the starting address, and pin number 3 means I need to mask the bits in similar manner, right? So the lowermost 2 bits are not to be used, and my starting 0th bit will be here, first bit will be here. So this will correspond to pin 0, this will correspond to pin 1, this will correspond to pin 2, and this will correspond to pin 3. So pin 3 means the address would be, if this I have to read this is going to be 00100000, and this particular representation would be 0x20. So I need to add an offset of 0x20 to this particular address, and that is how I get this as 0x400250020. So I can directly access pin number 3 using this particular address. So that same thing has been explained here. So you can see why we have got the address as 0x400250020. Now coming to how exactly the TM4C123 microcontroller, which is a part of the Texas Instrument Tiva C series, has inbuilt features for performing the interfacing with the LED. So there are basically 3 LEDs, red, green and blue, and there are 2 switches, and for LED interfacing we are using the port F, so that is why I explained only the addresses corresponding to port F. And we are using the port F pin number 1, 2 and 3 for the interfacing purpose. Now if you look at the pins, the way they are connected, you have a digital transistor and this is the LED that has been provided. So this digital transistor is basically an NPN transistor, and it has the built-in resistors, if you observe here, which are allowing it to function simply as an on and off state, either in the saturation region or in the cutoff region. The purpose of this particular transistor is to prevent any excessive current flow that could probably damage the GPIO pin if it can't handle that current demand. So when the GPIO pin outputs a particular logic signal in order to drive this particular LED, the transistor will take on the load, protecting the GPIO. Now we have seen earlier in the slides that GPIO pins for port F are 5 in number, and we in particular are going to be using only 3 of them for the LED interfacing, starting with pin number 1, 2 and pin number 3. So if you see the table here, in particular corresponding to a particular pin, we have the color that are defined. So for pin 1 it is the red color, pin 2 it is the blue, and pin 3 it is the green. So when you are providing the values or trying to enable a particular pin, you should be able to glow the right color LED. So when we are writing the code, we are providing this values based on which color we want to glow. Okay, so if you see here, I have pin number 3 of port F being given to green color, pin number 2 being given to red and to blue, and pin number 1 being given to the red color. So if I want to glow the green color LED, I need to provide a value of 0, 1, 0, 0, 0. And how these are given is because port F has 5 pins. So we'll start with port F0, port F1, 2, 3 and 4. So if you observe, the port F3 corresponds to the third bit position, so that is why the address is 0x08. Similarly for blue color it is 00100, that is 0x04. For red color it is 0x02. And if you want to glow all the 3 LEDs, the color combination would be in such a way that all of these pins have to be set high, and that is when you get a white color with the value 0x0E. Similarly, you can have 2 LEDs being glowing, just 2 LEDs, and that is dependent upon the color formats. So if you see here, green combined with red will give you an yellow color. So make sure that you enable those pins only. Blue with green will give you the magenta, and red with blue will give you the cyan color. So depending upon which color you want to glow, you need to set the corresponding values. So that is why the addresses are in this particular manner. You can choose how many ever LEDs you want to glow. Here we have been provided with 3, and those main important colors are red, blue and green. Okay, so we have discussed this already. We have seen what steps we need to do. Let us go to the programming part. So since we are performing interfacing here, we will be writing the code in C. And this is not the only way in which we can perform the toggling of the LED. You can just make use of the header file and write the code, which would be even more simpler. But this is just an example to explain you that how exactly we are going to make use of the various registers that we just looked into, and how we can define those registers to make sure that we are able to understand the process of how to configure them. So as we said, we will always start the configuration of any GPIO pin with the clock configuration. So what we are doing is we are defining the system control, and as I told earlier, we will be using the RCGC GPIO register for this. So if you observe, we have a pointer here and we have another pointer here, and this particular address is specifically meant to enable or disable a clock for the GPIO ports. And what does this volatile signed long says is that it is basically to indicate that the register is 32 bits wide. So that is why we make use of the term volatile unsigned long. So this particular pointer is used because it's an indication that it is a pointer to that particular address, and this is a memory mapped address. So this is an indication that this is a pointer to this particular address. And if you observe, there is an asterisk symbol here as well. So this asterisk symbol indicates that it is a dereferencing the pointer, which means it is allowing you to directly access the memory location 0x400FE108. So this is a pointer to this particular address, and this is basically a dereferencing pointer. Okay, so the first register is meant for enabling or disabling the clock, and then we define the register in particular to the port F. So for a port F, if you observe, we have ports A, port B, port C, port D, port E, and port F, right? We want to mention that we'll be using only port F, and that is why the address is 0x000020, because we have enabled only the bit 5 because it corresponds to port F. Then the next step, if you remember in the configuration, is to choose the mode control, and for the mode control we are using the GPIO data register. So if you observe here, GPIO data register is used, and this is a name that we have defined because we are using port F, right? So that is why I have highlighted this in particular in blue color to indicate that the data register name is modified for us because we want to show that we are using the port F. Then again things repeat. This is a pointer to this particular address. This is dereferencing pointer. Volatile unsigned long means it corresponds to a 32-bit register. And since I want to access only the pin number 3 of the port F, I am having the address 0x4002520. Now I explained you how this address has come. So if you remember, for a port F, the starting address was 0x4002500. If you are using pin number 3 in particular, we are making use of an offset of 20, that is why the address is 25020. Then we define the direction, whether we want it to be acting as an input or whether we want it to be acting as an output. So that is why we have this particular address. Now how this address is obtained is, we have the base address. So the base address is for the port F is 4002500, plus we have added an offset of 0x400, and this offset is based on this particular table. If you want to enable the data control registers, in particular the GPIO direction register, the offset that needs to be added is 0x400. So that is why, if you observe, that particular offset is being added to this base address. Then we need to digitally enable the port F. That means we have to set the bits. We want to make it to act as an output. So that is why we have used the address 0x4002551C. Again, this offset is based on the table. For pad control registers, in particular, if you want to digital enable, you have to add an offset of 0x51C. That is the digital enable register. So as you observe, this is the address that we obtain. Then we specify the system clock frequency, which is 16 megahertz in our case. And this code, if you observe, is meant only for toggling one pin of the LED. Okay, we have to modify this particular value that we specify to the pins. Based on that, automatically our glowing of the LED colors also will change. So then we provide a delay. We don't want it to be constant, right? We want it to blink after a certain delay. So that is why we are dividing the system clock frequency by some value. And this value can be changed depending on what value we give, a higher value or smaller value. The blinking of the LED could be either faster or it could be slower. Then comes to defining the pins. Now I have explained this, why this is 0x08. This is 0x08 because we want to glow the green color LED, and we can choose any color. So based on that, which color you want to glow, you need to change the value as mentioned here. Then we specify a variable. We want it to be unsigned, j to be equal to 0. This is specifically meant for the delay loop. Then we need to do the configuration. Whatever GPIO port F clock we want, then need to configure it, right? So that is why we make use of this particular symbol, which corresponds to setting specific bits. And it is more like performing the bitwise OR operation. So that is why we are doing ORing. We need to use the GPIO port F pins only for the digital enable as well as for the direction for setting them as output. Then we give it a loop. We want the blinking of the LED to be on a continuous basis, so we provide a while loop. And here if you see, we are using the GPIO port F data R register, wherein we are directly accessing those pins and we are performing an XOR operation. The XOR operation is performed because we want to toggle the LED. So if you observe the XOR truth table, for a combination of 0 0 we have the output as 0, 0 1 is 1, 1 0 is 1, and 1 1 is 0. So we want to toggle it from 0 to 1 and 1 to 0, and this has to be continuous. So that is why we are making use of XOR operation. So this is done on the mode control register that you see here, that is the data R register, for directly accessing the pin. Then we provide a delay loop. So for j is equal to 0, j less than delay, j plus plus. So this code will make sure that your LED is going to be toggled, and here in particular we are using only the green LED. So you can change this accordingly the way you want, so that you can observe for different color combination. So here is the program for LED blinking. So first what I will do is I'll make sure that my clock configuration is ticked. So I'll go to the configuration wizard and make sure it is ticked. After that I will build the code and then click on load after I ensure that there are 0 errors and 0 warnings. So once you load, make sure that your USB connection is given. Then only the loading will be proper. So that is why there is a USB cable that is connected, so that the microcontroller can be connected to the CPU. So I will provide the connection and ensure that the kit switch is on. So if the connections are proper, your kit will start showing the power on connection. So I will reset the pin and you can see my LED is glowing. Now I'll make some modifications in the code. So currently what I did was, in the code I have provided the value as 0x0a, which is 1010. That means my green and red color LEDs are on. So I'll make modifications to this. I will change it to 08, and now my only green LED should be on. So I will save it and then load the code. Finish loading, and now I'll press the reset once again, and I can see that my green LED is on. Now in the kit, the 3 LEDs are placed very close to each other, and that is why even when you press multiple or try to glow multiple LEDs, they will appear like as though only single LED is glowing, but that is not the case. So I will change the configuration once again. I will make it to 0x02 and load it and reset once again, and I can see that another different color LED is glowing. If I want to glow all the 3 LEDs, then I would have to give a combination of 0x0e so that I get a white light, because all the 3 R, G and B LEDs are on. So I will load it once again and press the reset button. So here you can see the white light is glowing because all the 3 LEDs are on. So we can have a single LED glowing, two LEDs glowing, or multiple LEDs glowing. And we can also change the delay in which the blinking occurs. So for that, what we will do is the delay value system clock frequency, which is now divided by 10, can be divided by 100, so that we provide a small delay and we can observe that our LED is blinking or toggling at much faster rate. So I'll press the reset once again, and you can see the LED is glowing at a faster rate.